So today we're going to talk about the fourth principal technology of avionics, or aircraft electronics. Analog and digital electronics is all the same. It's taking over everything. It's taking over your car. All the things in red up here are things that I will hold you responsible for. So you should know what those things in red are. In other words, aircraft electronics, another word for it is GNC. GNC is guidance, navigation, and control. Those are standard words in the aircraft industry and in technology globally, actually. Now, what does the G mean? Well, the G means I have something is giving me situational awareness. So I know what my attitude is of my aircraft, and what's that? My attitude is my heading, which way I'm heading, what my pitch axis is, and my roll. So I know my pitch, heading, roll, and if I do that, if I know that with respect to ground references, right, or flight references when I'm flying, then I say I have situational awareness and I've achieved adequate guidance. Because our position, velocity, and time now with respect to the Earth is all described by satellites. All of it. Everything. So that's something new. In the old days, you'd get a map. You'd make sure the map was good for your area. You'd go hiking up in the hills and you'd see where the elevation was. You can no longer do that anymore with stuff that comes from space. And we'll talk about navigation and how this creates all kind of problems when you're flying around here. Finally, we'll talk about control. Control is what causes good flying qualities. So we'll talk about this in a later lecture, flying qualities. But basically, stability and performance relative to a defined mission. And we'll give you some examples of fly-by-wire. So what fly-by-wire does is it disconnects the pilot from the controls. In the old days, if you go fly a small airplane, there's a cable that hooks you up to your controls. And that cable actually moves through leverage. It moves the control surfaces. That's pretty much gone. That went with hydraulics. Hydraulics came in, I don't know, in the 60s, late 60s. And it put, now all of a sudden the pilot is giving a command to a hydraulic actuator. The hydraulic actuator is pumping high pressure hydraulic fluid to the control, and it's moving it, right? So that was a big change. That was a big acceptance for the pilots. And the first aircraft I flew, the 141 that came online around 1966 or so, it had backup systems. It had electrical roll control with electrical motor, and it had everything was a backup. Now those backups are gone. It's all hydraulic. Plus, they replaced a lot of the hydraulic lines with computers, so the computer actually sends a signal somewhere to control the hydraulics. So now you got two different systems in between you, and you're not sure exactly what you're doing when you're pulling on the stick or moving the control wheel. You're generating some kind of an electrical signal. That electrical signal is going to a hydraulic actuator. Hydraulics move the control surface, and you hope it flies the way you want. So everything is kind of a little bit different. It's in the cockpit like this, and if I pitch up, then the ball goes like this. It just shows me a pitch up. If I roll, the ball goes like this. It shows me I'm rolling, right? So that little ball moves around in the cockpit, and you can see the links, the numbers 10, 20, and there's 10, 20 degrees for roll. So here's the roll axis. Here it shows you the pilot what his bank angle is, and there's the pitch axis, shows you how high up he's moving. The little W means landing gear. So it's kind of saying, well, I'm looking at the airplane like this, and it's got its landing gear like that, and I'm pitching up and I'm rolling like that. So that's the attitude you would see. And that's called your attitude indicator. It's also good to know which direction you're headed. So you come down here, that's the attitude indicator. This one is called a horizontal situation indicator, or HSI. It's basically a compass, right? So over here, you're looking at your heading over here. So this aircraft is flying north, called a Mercator projection that pilots use. So pilots can use a map that's flat, and when they stick their ruler on the map to plot an angle or a course, they get the right angle that they can fly. Wait a second, that's a true course, but I need to fly a magnetic course. So the pilot needs to make another correction to correct from the true course of the map to the magnetic course. These are called instrument landing systems, or ILSs. Any pilot would know what you're talking about. If you talk about an ILS, they're all over the place. Every big airport has one. And what it does is it sends out two beams. One of the beams is transmitted locally, like here from San Luis. Sends out a localizer beam. And then that's what gives you the little bar in the cockpit that tells you whether you're to the left or to the right. That localizer being set. And you dial it into a frequency, then you pick it up and you fly, and that will give you left or right. There's also a second transmitter called a glide slope. And the glide slope transmitter has its own set of frequencies. So you dial that into, and then that tells you whether you're above or below a desired glide path angle, which is normally around 3.5 degrees or so. So if you dial in both these frequencies, you'll get the bars, and you can fly right down this, even if the weather is totally socked in, you can't see outside the car, or outside the aircraft. You can fly right down this. That's called flying the localizer and the glide path. And you might be missing one of these signals. So then you'll have a localizer only approach, or a glide slope only approach, and that means you can't go quite as low as you could if you had both of these. The satellites from GPS have changed what we wanted to do, and it's taken a decade or so to kind of infiltrate to the pilot community. So what the GPS does, the global satellite does, is they have something called wide area augmentation. And this wide area augmentation kind of takes the place of these transmitters. They're satellites in space, they're extra satellites in space that give you a correction to GPS. So your GPS signal is only about 1 meter inaccurate, 1 meter. So a pilot flying with GPS WAPs has got about 1 meter accuracy. Your GPS on your cell phone is about 10 meters. So it's about 10 times better. And that allows him to go lower and slower. So if he's flying this technology. And the approaches change. If you're flying a full-up localizer transmitter approach, that's called a precision approach. You can actually go almost down to touchdown, right? With 0-0 weather, you can't see out inside. You can still land the aircraft with a full precision approach. If you're flying off satellites, however, they are called non-precision approaches, or they call them LPV, localized performance with vertical information. And then you can't go quite as low. But it looks the same in the cockpit. The cockpit gets the same bars, just like it was an ILS. It's just that the pilots have to realize I can't go quite as low when I'm flying the GPS approach as I can with the full ILS. Why don't I just keep the ILS with the precision approach? Why don't I just keep that, right? Well, because you need a 2-mile runway, the FAA has to monitor it, and you need big bucks. What do I need to shoot the satellite approach? A runway, somewhere, anywhere. Farmer John out here, right? You can shoot an LP approach anywhere that's got an appropriate runway for your aircraft. How do I get this onto a map that I show the pilot, or that you use when you're hike, or into your cell phone? How do you get this map onto here? And this is where it can get very complicated. But I want you to remember what I said at the start of class. The way we do that is we preserve the angles. We preserve the angles so that it kind of looks right. Our brain will accept the difference in scale. We don't care that Brazil isn't anywhere near the size of Brazil when we. So wait a second now. We were talking about the Earth, and I kind of said the Earth looks like a mathematical ellipsoid, right? So you're kind of the GPS satellites. But now he's talking about a geoid. And what the hell is a geoid? Well, the geoid is a very important thing that sensors use called inertial guidance systems. Inertial guidance systems are used on our weapons, they're used on our navigation and our military system. They're totally passive, they can't be jammed. And when GPS goes away, the inertial navigation systems will still be working. So it's very important. However, the inertial navigation system navigates with respect to what's called a geoid. Now this is what a geoid is. I'm just going to probably tell this once. And if the Earth was only rotating, right? It was only had all water. It just had water, and there was no moon. Get rid of the moon. So there's no tides. There's no tides, and there's nothing but water. And the Earth is still rotating as it's rotating, but there's nothing. There's no land to stop it. There's no shoreline. There's no waves. It's just steady, and there's no moon. That's MSL. That's mean sea level. Okay. Now let's bring the moon back. The moon comes back in, and it's rotating around the Earth, so it's sucking the waters around, so the tides go high and the tides go low. So you have a high tide above MSL and a low tide below MSL. That's all with respect to the geoid. right? The geoid is what gravity would be if there was no landmass on the Earth.
This model is widely used by all.
That's what it looks like.
It's been calculated previously, but never with the precision that you can see.
Does that make sense? The satellites define the zero height level of the ellipsoid as the MSL level of the geoid. So you need to know that conversion for your height. So you might get your XY position relatively accurately, but if you want to know your height, you have to convert it from the geoid to the ellipsoid, or the ellipsoid to the geoid. And then you have to know the conversion from the geoid to the surface for where you're at. So you need a local map. So let's review. Our maps are Mercator projections that we have true. So true is good on the maps. The horizontal positions come from, they must be corrected from the geoid to the map or from the ellipsoid to the map. That has to be converted. Okay, so the coordinate system that the GPS uses is hooked up to the Earth as the k-axis. It goes around the Earth's axis. The k-axis goes up through the top. So the Earth rotates about the k-axis. And the I and the j-axis are in the equator. And one points towards the equinox, and then the other one is 90 degrees off. So that gives you an IJK system in what's called the Earth-centered Earth fix. And that's what you need to remember. That Earth-centered Earth fix defines the ellipsoid. That coordinate system in meters, because GPS just keeps measuring time. It never changes. So right now, GPS and what's called Zulu time, you can think of this as Christmas time. And on Christmas Day, every year the Earth's at the same spot. That's Zulu time, or Universal Coordinated Time, or IRIG time, or Mercator time. It's all standard time that we use at midnight. How accurate is GPS time? Within a nanosecond. What's a nanosecond? It's 1/10 to the minus 9th second. What does that mean physically? Can I have an idea? Yeah, a nanosecond is the time it takes light to travel 1 foot. Right? Light goes 186,000 miles a second. Well, in 1 foot, light goes 1 nanosecond. That's how accurate. Here's what a cockpit looks like. There's your airspeed indicator, airspeed. And there's your attitude indicator. Remember we saw this is what rotates, pitch up and rolls. That's your altimeter. Every rotation is 1,000 feet going up. That's your turn indicator. Tells you to turn. Here's your compass right here. So this compass, if I were at this is how the runway looks at San Luis. It's runway 29, and runway 29 means that it has kind of a magnetic heading, of 290 degrees. Now, why do I say kind of? Because on a map, if I just it's 303 degrees actually, but it's you have to subtract with our variation, which is 13 degrees east, from 303 to get approximately 290 degrees. And this number is always changing. It's always changing. So what happens, and this is how it shows on a pilot map. A pilot will look at a map of San Luis Obispo and he'd see 14. So he'd take the true course that he measures with respect to that line, subtract 14 degrees, and that's what he would read in his heading indicator to fly along that line. This is how the magnetic north has been moving. Look at that. There's the actual, that's true north, and there's magnetic north. Look how it's been moving all around the place. And like I said, they moved 30 kilometers last year. It's accelerating for some reason. We're not exactly sure why it changes. Use our airport as an example. Our airport runway is 303 degrees, right? That's relative to the Earth rotation, fixed axis, never changes, right? The variation right now is kind of given as 13. Maybe it's 14, maybe it's 15. The magnetic course moving. So if you subtract the variation, you'll get runway 29. That's the name of the runway. The name of the runway is this magnetic heading. That's what a pilot would fly to line up with the runway. That's when he takes off, he looks at his heading, and that's 290. It won't be, because it'll be off a little bit because the magnetic north has been moving. When it moves by 5 degrees off, they'll rename the runway. They will rename the runway. And that should happen in a few years. So if you come back here, when you're my age, you come back and say, oh, it's runway 295. It was runway 29 when I was here. You know, that actually could happen, would look like. The problem is, typically, these things can generate confusion. We're not sure sometimes what these systems, look how complicated the system can get. And if they start doing things that you don't understand, you can generate a lot of confusion in the cockpit if you haven't been trained on it. So when we flew the RV-7, when we built the RV-7 and flew it, it has an electronic cockpit display like this. And it went black on me once. The display just totally went black when I was flying. Well, but now you have nothing. There's nothing. I mean, I had to go by the sound of the engine to what RPM I thought I was at, right? I had no idea what my airspeed was. So I came back and landed, and when I'm taxiing in, I noticed that somehow I had hit the night button on the light. So the aircraft thought it was night out, and it dimmed the display. So it wasn't broken, it just had dimmed to the point where I thought it was out. But that's, I mean, having experienced that kind of thing kind of gets your attention.
This giant Airbus. Though there are 700 in service, there hadn't been a single passenger fatality until Flight 447. This history of reliability rests on a highly computerized flight control system. The flight computer won't carry out any pilot command that endangers the safety of the aircraft.
Okay, so let's just stop right there. Right? Okay, I already gave you the example of my example of what could go wrong, and so that was the good. This kind of is going to be the bad here of fly-by-wire flight control. Why didn't the airplane? Heard the guy say that nothing can go wrong. Nothing can go wrong. So, but here's what happens. Typically, this happens is the pilot in the cockpit will see something he doesn't like. He'll move the stick, and then the computer, there's a little bit of a time lag. It doesn't seem like much unless you're doing something that takes a lot of, unless you're into the loop, you call it. You're moving, you're landing. So you're moving the controls a lot, and you don't see any motion. So you move the controls more and more. You start moving, and the airplane's lagging. It's lagging you. So what you should do is stop. Like he said, take your hands off it, let the airplane settle down. But if you don't, as you saw in those examples, if you don't, what happens, remember the hydraulic system? Right? These are huge controls on these fighters and airliners. They're huge. The space shuttle, they're huge. So you're using all the hydraulic pressure. If you watch the hydraulic pressure, it would go like this, woo, it's zero. But what happens when the hydraulic pressure goes to zero? And you're doing this in the cockpit? Nothing. There's nothing moving the control surface. The pressure is zero. You got to wait for it to build up. So you see the pilot gets behind the aircraft, and the aircraft, if they're unstable like most fighters, or even the airliners are very close to unstable, they'll take off on their own. They'll just fly the way an airplane's going to fly, which is always not good now in modern times. So they crash. So you have to be very careful. It takes a lot of knowledge of the systems and the training and the pilot lags, watching these examples, and never taking something. That's a Nova show that we watched and said, oh, the system will never let you do anything wrong or bad. Yes, it will. You can deplete the hydraulic pressure under certain circumstances, or if something depletes your hydraulic pressure, then you better have a backup plan of what. So that's what I wanted you to know today. This is a good recap. This is a good view graph to take with you into the test. This is basically just a review of what we've talked about. Position, velocity, time, magnetic, true course, control, fly-by-wire, what it all means. And it's kind of a technical, this is a technical part of the class. So there's your quiz for today, and you got 10 minutes to do it. So we'll turn it in today.